Okay, so hello everyone. Our next topic is Gauss elimination. How can we solve a linear set of equations? Uh, what are the techniques that can we use? Okay, so remember that we may have a linear set of equations. In fact, when we are talking about the linear set of equations, we have constants a11, and here the a's are the coefficients and x's are the unknown variables, and then we have the right hand side, so b. So here x1, x2 and xn are the unknowns. As you see, they are common in all equations, in all of the equations. And then we have the coefficients. So when we are talking about the first equation, the coefficient of the x1 is a11. So the first index tells me that it is the first equation and it is the coefficient of the first unknown. Then I have the 1, 2, a12. So first equation and coefficient of the second unknown. And it goes like this, of course. So I have a1n, and indeed it is the same for all equations. Now, in order to solve a linear set of equations, if you have n number of unknowns, certainly you should have n equations. Now, the fact is they are linear because, as you see, the unknowns are not multiplied by each other. They are summed up in general. So this is how we define the linear set of equations. Okay, so let's see how we can solve it. Of course, when the number of unknowns are small, you can use graphical methods. And certainly, if in many cases, if the number of unknowns are 2, so if you have 2 unknowns and 2 equations, as is the case here, okay, for example, here we have a11 multiplied by x1 plus a12 multiplied by x2, then that's equal to b1. And in fact, it is the same for the second equation. We have a21 multiplied by x1 plus a22 multiplied by x2, and that's equal to b2. Now, I can think that x1 and x2 are the x's. You can choose any of them. So it's like saying that one of the variables are x and the other one is equal to y. So let's say that it here, for example, we have the x coordinate for the x1 and saying that for the x2 it's equal to y. So then we have an equation in x and y. And here I can obtain the y as a function of x, as is the case here. Now we have 2 functions. So the first one is this one. As you see, what I do is I divide the whole expression, the first equation, with the coefficient of x2, that is a12, and take all the expression, then the rest of the variables, to the other side of the equality. Then I will obtain this function. So it is minus a11 divided by a12 multiplied by x1, then plus b1 divided by a12. Identically, I can do the same operations for the second equation. First, I divide the whole equation with A22, that's the coefficient of x2, because I consider that x2 is equal to y. And then I will take the expression to the other side of the equality. Then I will obtain this function. x2 is equal to minus a21 divided by a22 multiplied by x1 plus b2 divided by a22. Now certainly I have two lines here, as you see. So this represents one line and the other one represents the other line. I can draw them. So remember that I have to find two values, so x1 and x2, such that these values have to satisfy both of these equations. Now this is only possible when we draw these two lines, x1 in one axis and x2 on the other axis. So we will have two lines, and certainly the intersection of these two lines will give me the solution for these equations, for the two equations. So therefore I need to find the point where they intersect. This is the graphical method indeed. So here, for example, we see two equations, minus x1 plus 2x2, and the other equation is 3x1 plus 2x2, that's equal to 18, and the first one is equal to 2. Certainly they intersect at a point x1 is equal to 4 and x2 is equal to 3. So this is the graphical method. Maybe you can apply this technique for three-dimensional with the equations with three unknowns, but for the higher or for the equations with more than three, this type of approach most probably will be problematic, because we cannot figure out the spaces which has more than three-dimensional, in fact. Okay. So this is the graphical approach, but this helps us in understanding the nature of some methodologies and the set of equations. This is the thing. So let's have a look. If, for example, you have two equations and you draw them in a graph, then these two equations are parallel, as is the case here. There is no solution because they do not intersect. So the distance between them are constant. As you see, the coefficients of x1 and x2 are the same, but only the right-hand sides are different. As a result, these two equations represent the lines which are parallel and they do not intersect. What else? Certainly we may have two equations which are linearly dependent, as is the case here. For example, first equation is -1/2 multiplied by x1 plus x2, and that's equal to 1. And the second equation is x1 minus x1 plus 2x2, and that's equal to 2. Now, either I can multiply the first equation by 2, or I can divide the second equation with 2. Both are okay. Indeed, these two equations represents the same lines. As a result, I have infinite number of solutions. This is what it means. So there are infinite number of x1s and x2s. What else? Okay, in some cases, problem or set of equations may be ill-conditioned. Sorry, I didn't write it carefully, so it is ill-conditioned. So let me write it again. Okay. So it's ill-conditioned. What does ill-conditioned means? Now, this set of equations are different. For example, let's look at the coefficients of x1 here. It is minus 2.3 divided by 5, and it is minus 1/2. So there's a little deviation of 0.2. So if it is minus 2.5, these two sets of equations will represent the same thing. And also we have here a very small deviation. For example, it is 1.1, whereas in the second equation it's 1. So the numbers, the differences between the coefficients and the right-hand side are very little. Very little. And remember that in computers, we have round-off errors, chopping errors, and so on. Sometimes these small differences may be critical because we generally use computers to solve large set of numbers. And if these small differences, sometimes these small differences may cause may drive us in difficult situations, so such that we may not arrive to the right solution because of the round-offs and choppings and all other errors. So this is what the case is. As you see, there is a very small difference, and the computer may not detect this difference. It's all about the precision. Okay, so this is how we define the ill-conditioned problem. Therefore, we may have problems without a solution. We may have problems which may have infinite solutions, or we may have ill-conditioned problems. There are several examples of ill-conditioned problems. For example, low Mach number problem is an ill-conditioned problem generally, because the Mach number is so small, and as a result, the computer cannot detect the small variations in fluid flow at low Mach numbers. Okay. There are, of course, techniques which we can solve this problem, which is called preconditioning. We can talk about it in the forthcoming lessons, maybe. Okay. Now, of course, there are several techniques, but first thing is we are dealing with the matrix algebra. Indeed, we can write a set of equations by means of a matrix vector multiplication. Therefore, we have a coefficient matrix A. Okay. So we can write all the coefficients in a matrix: A11, A12, A13, A21, A22, A23, A31, A32, and A33. But the good thing is As a result, then the unknowns will be the vector, okay, the column vector, and the right hand side will be column vector as well. Now, first thing is to calculate the determinant of this matrix. So there are some criteria, for example, in evaluating the ill-conditioned matrix. If the determinant of a matrix is very close to 0, probably the matrix is ill-conditioned. So this is one thing. And therefore, we need to calculate the determinant of a matrix. And we need to know how to calculate the determinant of a matrix. Here we see a 3 by 3 matrix. But first thing is, let's look at the submatrix, which is 2 by 2. We know how to calculate the determinant of a submatrix. Determinant of the submatrix is, so for example, consider a matrix A11, A12, A21, and A22. Certainly, we can easily calculate the determinant of matrix. First, we multiply these two elements, A11 multiplied by A22. And this gives us this value, A11 multiplied by A22. Then we multiply the two other, A21 multiplied by A12, and this gives me this term, A12 multiplied by A21. Then I subtract the first one from the second one. This is the determinant of a 2 by 2 matrix. Certainly, we can calculate only the square matrices. So what is a square matrix? So the number of columns are equal to the number of rows. Okay. Now, then what we do is remember that how we calculate the determinant of a larger matrix. I'm just giving it, and I will just give it through the 3 by 3 matrix. So first, we choose one of the rows. Perhaps the most simplest and the straightforward one is the first row. Sorry, let's choose the color red. Okay, so I choose the first row. Then I begin to give a sign to them. So the first row is plus. Then the second one is minus. Okay. And the third one is plus again. Now, I will exclude the first row and first column first. So this is my first column and first row. So the next thing is, now as you see, the remaining one is, I have a 2 by 2 matrix here. A22, A23, A32, and A33. Now, what I'm going to do is, I will take this value, A11, and take this matrix and calculate the determinant of it. Since I have a plus, I multiply it with the positive sign. So I multiply it with the plus 1. Then I go for the second member. So I choose A21 and I exclude the corresponding row and column that A21 is in. So I exclude this column and I exclude this row. Now I have a matrix here, A21, A23, A31, and A33. And I take this matrix. Then I multiply it with the A12. Now I have the minus sign for this operation and I put it here. Now for the third one, my member is A13. I exclude the corresponding row, so which the A13 is in, and corresponding column. So I exclude these two values and I take the remaining terms as a 2 by 2 matrix. So you have A21, A22, A31, and A32. Therefore, what I do is I take this matrix and calculate the determinant of it. I multiply it with the A13 and then I got the sign of it, plus. So as a result, determinant of this 3 by 3 matrix then first you take the A11, calculate the determinant of this matrix, and multiply it, minus you multiply A12 with the determinant of this matrix 2 by 2, and then you take the positive sign, and in fact you have A13, multiply it with the determinant of this matrix. If you have a larger matrices, what you need to do is then again you can choose any row, but possibly the first row plus, minus, plus, and then minus. Then the remaining matrices will be 3 by 3. Then you have to decompose this 3 by 3 matrix, calculate the determinant of the 3 by 3 matrix, and multiply it with the corresponding element of the original matrix. And it goes like this. So you constantly create submatrices and try to find their determinants and multiply the corresponding multiply it with the corresponding element. So this is how it goes. This is how we calculate the determinant of it by using algebra. Okay, so this is the approach for calculating the determinant. Now, our first method is the Cramer's rule. Perhaps you have seen it, but just let me remind you. Now, I will give it through the 3 by 3 matrix, but of course you can use larger matrices. So it can be a 4 by 4, 5 by 5, 5 by 5 matrix as well. And it's not that challenge. So first, I take the matrix, original matrix. So let's say that I just want to find the coefficient or unknown x1. I know that first row in the original matrix, the first column, the elements in the first column are the coefficients of the x1. So what I do is I replace all the coefficients in the column. In this case, since we choose to calculate the value of x1, so it is the first column, we replace the first column with the right hand side of the equation, values in the first right hand side of the equation. Now we have a different matrix. You see B1, A12, A13, B2, A22, A23, B3, A32, A33. Okay, so we have a new matrix. And we calculate the determinant of this new matrix. Then we divide it with the determinant of the original matrix. This gives us the value for the x1. If you want to calculate the second unknown, x2 for example, then you have to replace the second column with the right hand side, with the values in the right hand side of the equation. So it is A11, A21, A31, and here it has to be B1, B2, and B3, and then the rest is the same. So you calculate the determinant of this equation, and then you divide it with the determinant of the original matrix of coefficients. This is what we call Cramer's rule. Okay, so this Cramer's rule is the second technique that can be used in finding the coefficients.